So today I want us to look at the concept of parameter and the statistic. These are relatively concepts we have been using in our classes. They are not new. And when we talk of a parameter, we will say that it's a numerical characteristics for an entire population. Because in research, we usually deal with a sample and we deal with the entire population. So when you are dealing with entire population, then we refer to the numerical characteristics for the entire population. And when you talk of statistic, is in a numerical characteristic for a sample taken. So when you are dealing with a sample, we refer to a statistic. And when we are referring to the population, a numerical characteristic, which we get, we are able to refer to that one as a parameter. An example here, if I want to know the mean age of all the teachers in Kenya, that is the population, and the symbol for population is mu. Then if I want to get the mean of a random survey, that is simple survey, taken from a just pet of teachers, then we will be talking of a statistic, and this one is represented by X with a bar on top of it. When I want to compare the two, or when I have to compare the two, the mean, which is taken from the population, has a mu as a symbol, and the statistic has an X with a bar. And when we are calculating the standard deviation, the symbol is a D, but it's not a D. And for the statistic, the symbol is S. For variance, it is delta squared, and for variance of the statistic is S squared. Both, when we are using the proportion of the population, then for both of them we'll take P and P. And for their formulas, the formulas will be a little bit different. And you can see the formula here is delta equals to root of summation of values of X minus mu, both squared, all over n. And for that of statistic is root of summation of X, values of X minus mean, both of them squared, all over n minus 1. So you can see that when we are talking of the parameter and the statistic, we are talking of the same thing, but they are taken from a different, for a parameter, it's taken from population. So when you are talking about parameter, you are referring to the population. And when you're talking about statistic, you are referring to a sample drawn from the population. And some of this, we are going to be using these ones. You'll be seeing the difference as we go on with the lesson. Now, the other thing I want to look at is the variability and sampling error. Now, when you talk of variability, sampling variability, it is how much an estimate varies from the samples. Now, when we are talking about sampling variability, we only refer to statistic, the number generated from a sample, and never the number generated from a population. But when you're talking about sampling variability, don't refer to the population. We will be referring to the sample. And also, closely related term and almost synonymous, it is sampling error. And I would say that an error in sampling isn't a mistake, but it's a measure of how a value differs from the true value. And we saw the other time that increasing or decreasing the sample sizes leads to changes in the variability of the sample. Now, the difference between the measured or computed from a sample, that is a statistic, and the corresponding measure computed from a population, which is a parameter, is what we're calling a sampling error. So the difference between the sample and the difference between the population, the parameter, when we get that difference, is what we're calling a sample error. Now, in a population, we might get so many samples in a population when we are doing sampling. For example, if I have a population of 1,000, from that population, I can draw several samples from that. And when I get the mean of those samples, I've drawn, is what we usually refer to sampling error of the sample mean. Because there are several samples I'm taking from the population. Then when I get that sample and I get the mean of those samples I have gotten, it's the sampling error of the sample mean. And it said that when you take as many samples as possible from a possible population, and then you compute their mean, or you draw the histogram of these, means you have taken, you realize that most of these mean you will, when you draw that histogram, it will form as some sort of a normal curve. Now, we will come to that one later, but I will continue by saying that a sampling error is a statistical error that occurs when an analyst does not select a sample that represents the entire population of the data. And as a result, the results found in the sample do not represent the results that will be obtained from the entire population. There are types of sampling errors. One is population-specific error. And the population-specific error occurs when a researcher doesn't understand whom to survey. And you've done some research at your master's level. The people are looking at your work, they were very specific, and they were asking, what is your target population? Because if you miss it out, you will be getting an error in this area. Then another error is selection error. Selection error. In this selection error, occurs when the survey is self-selected, or when those participants who are interested in the survey respond to questions. Researchers can attempt to overcome selection error by finding ways to encourage participation. You know, in this kind of research, people who are interested only respond to the questions. But those who are not interested do not respond. Also, another error comes as a result of sample frame error. You look at your sample frame, and the sample is selected from the wrong population data. You have your sample frame, but when you go to select now your sample, it's selected from a wrong population data. Then we have non-response error, which occurs when useful response is not obtained from the surveys because the researchers were unable to conduct potential respondents. So those are the types of sampling error we have. Then I'll move on to look at on how we can be eliminating the sampling error. We looked at it on the other time, and we say that we can reduce the sampling error by increasing the sample size. And we said as the sample size increases, the sample gets closer to the actual population. And this reduces the potential for deviation from the actual population. Also, researchers attempt to reduce sampling error by replicating their studies. And this is done by doing the measurement repeatedly. You use more than one subject or a multiple groups when you're undertaking those studies. Also, when you do random sampling, you minimize the occurrence of sampling error. So random sampling, other than going for these other methods, random sampling reduces on these types of error. Now, some people will say that error is wrong, but why is sampling error important? Being aware of the presence of sampling error is important because it can be an indicator of the level of confidence that can be placed in the results. Sampling error is also important in the context of discussion about how much research results can vary. Now, when you want to get the sampling error, the formula of sampling error is equal to Z, equals to Z times standard deviation all over the root of the number of the sample size. And Z scores based on the confidence level, it's approximately 1.96. So when you want to get the sampling error, just take Z, which is approximately 1.96. And then you look at the population standard deviation, then the size of the sample size. Now, how do we determine the sample size? The other time I was asking that question, and guys were telling me that 30% of the population is enough. There's many approaches used by many people in determining the sample size, and I've only taken 4 which are commonly used. One is using the census for a small population. 2, imitating a sample size of similar studies. And 3, using published tables like the one I showed you the other day. And 4, applying formulas to calculate the sample size. Census for small population. If you have a population of 100 or 200, this is small enough. You don't need to do sampling if you have such a population, or a population of 50. You don't need to do sampling. You just use that small population and it will be actually equal to the census, because you'll have counted or accounted for every member of that population. And this one will give us the precision that is desired in that population. Number 2, using a sample size of a similar study, you look at some studies that have been carried before, and you look at the sample size of such a studies, and you use the sample size of such a study. But the problem with this is that you are going to repeat the same error that were made in determining the sample size for that study. That is the problem for this. Number 3, you use published tables like the one I showed you the other day, Morgan and Krusji. They had a table. We have several of them. There are several others that have published several of these sample size tables. You look at the population and you look at the sample size that is given. And you look at that population, at that sample size at a given confidence level, and you are able to use it. And finally, formulas for calculating sample size are used. There are several other formulas. Statistics books give us these formulas. And you can, as I told you the other day, look for them and see these formulas, how they are applied of calculating a sample size from a given population. One of such a person is Cohen's power formula. Cohen's power formula. It gives on how you systematically on how you can move from point A to up to the last point on how to calculate for the sample size. Then we have net resource equation. This one, when you're doing the scientific experiments. And also we have determination of sample size by cumulative distribution function. I've taken these 3 because they are the ones that are mostly used in calculating the sample size. Then let us look at finite and infinite population. When we talk of finite population, we mean that we can count members of this population. And it is also called countable population. And an example I'll give you here are vehicles passing on a given bridge. You can count them 1, 2, 3. So countable. And the number of units in a finite population is denoted by capital N. Now, sometimes it's not possible to count all the members of a population. Like you cannot be able to count the number of germs in the body of a sick person. This one is called an infinite or uncountable. So when you'll be doing our sampling, we know that there are finite population where you can count. When you're doing your sampling, you know that from the finite population, you'll be able to take this number of this countable number of the sample, and on uncountable number, what number represents, we use proportions. We use proportions. Another thing I want us to look at is the distribution, sampling distribution of the mean. As I said earlier, when I was talking about the sampling error, we saw that we go in the population and we pick out of that population a sample, so that we can study this sample, and we are able to get the characteristics of this sample, and we apply the characteristics of the sample to the entire population. Sometimes a random sample selected from population will not perfectly match the population. Thus, the sample statistic is not equal to the population parameter. Now, this sample we have selected, it is not the first and the last. There are several other samples we can get from this population. Now, as we continue selecting the samples from the population, these samples will might have different means, because you have sample A, sample B, sample C, and then you consider the mean of this sample you have selected from the population. In theory, if you are to select all possible random sample of a given size and compute the sample means for each one, this mean will vary above and below the true population mean. And if we graph in an histogram these values, the graph will be a sampling distribution. Now, for any population, the average values of all the possible means computed from all possible random samples of a given size from the population will equal to population mean. And this is expressed as mu x minus mu y. Now, when the average of all possible values of the sample statistic equals to the corresponding parameter, we call the statistic as unbiased estimator of the parameter. When the average of all possible values of the sample statistic equals to the corresponding parameter, that is the population mean equals to this sample statistic, it's called unbiased estimator of the parameter. Also, for any population, the standard deviation of the possible sample means computed from all the possible random sample size n is equal to the standard, is equal to the population standard deviation divided by the square root of the sample size. And this is shown as standard deviation X equals to the standard deviation of the population over the root of the population size, which is N, as shown here. Also, one thing to note is as a sample size increases, the distribution of sample means will become shaped more like a normal distribution. As we increase the sample size of any given distribution. For example, if we are having a sample size, a population of 1,000, and we increase the sample size from, if we took the first sample size 20, and we took the second sample size 30, we take the second sample size 50, then 7 and so forth, we're saying that the distribution of the sample means will become more shaped like a normal distribution. Now, if this population is normally distributed with the mean mu and a standard deviation delta here, the sampling distribution of the sample mean is also normally distributed with the mean equals to the population mean and the standard deviation equals to the population standard deviation. And this is divided by the root of the sample, like in the formula we are seeing on our screen. Now, what are we trying to derive to? We are deriving to that point where the mean of the sample should be always equal to the mean of the population. And when this one happens, or when this one comes to that, it means that the population we are starting is normally distributed. Because if you deal with a population that is not normally distributed, it will distort the results of the analysis and the statistics you'll be using. So we are to look for a sample size where the population or where the parameter of the mean and the statistics of the mean are on at the part, or they don't vary so much. And when they don't vary so much, so we will be able now to use the results we have obtained for the sample to generalize those results to the entire population. But if we don't do that, we have the results that do not have the sample mean and the population mean are different, then we end up doing a wrong deduction, or we end up doing the wrong differential from the results we are having. So the researcher here will always try to have the sample mean and the population mean being closer to each other, so that, or the standard deviation of the population and the standard deviation of the sample also being close to each other, so that when you do the conclusion of the results, or you make an inference from the results, then when you generalize the result to the entire population, there will be no much difference that will arise. And this one brings us to the normal curve. Now, the normal curve is a continuous probability distribution that is symmetrical on both sides of the mean, so that the right side of the center is mirrors the image of the left side. And as you know, The normal distribution is also called the bell curve because the curve of its probability density looks like a bell. Now, a normal distribution is determined by two parameters, the mean and the variance. A normal distribution with a mean of 0 and a standard deviation of 1 is called a standard normal distribution. I want to check whether we are there in the class. Amadi?
Yes, Daktari, I'm in.
Okay, thank you. Welcome. Ismail?
Yes, thank you.
Doctor, I'm present.
Thank you. Justus Wabwire, greet us. And I want to hear your voice.
Thank you, Daktari. I'm available and I'm enjoying everything that is going on.
Okay. Pamela?
Yes, Daktari, I'm getting you well.
You are available?
Yes,
Thank you.
Daktari.
Thank you. Then we'll have Samuel. Are you there today, Samuel?
Yes, Daktari, I'm following.
Okay, thank you. So today I'm trying to emphasize on the mean of the population, the parameter. We call the parameter because when you are dealing with the population, we call the parameter mean and the statistic mean, that is the sample mean, should be close to each other. Or if they are not close to each other, we are going to receive what you're going to call sampling error. Because when you subtract that mean of the parameter from the mean of the statistic, then we are going to have trouble. When it's so big, then you can't generalize. You can't generalize these results to the entire population. And that's why we're supposed to be very careful so that we minimize our sampling error, that the mean of the sample and the mean of the entire population should be closer to each other, so that when you're interpreting the results of the research, the standard deviation of the parameter and the standard deviation of the parameter, the mean of the parameter and standard deviation of the parameter should be actually equal, close to one, close to the statistic mean. They should be closer to each other there. Now, I want us to look at the population, the normal curve and the distribution of the area under the normal curve. Now, before we go there, why is the normal distribution important? It is important because many continuous data in nature display this bell-shaped curve. And also it's important because parametric significance tests require a normal distribution of the sample data points. So those 2 points, because many continuous data, and we talked of continuous data when we are doing statistics 1, they display this normal bell-shaped curve in nature. And second, the parametric significant test we are going to use, or we are going to start about in this very unit, they require, one of the assumptions is that the distribution of the data is normal. Before you use them, it requires that the data is normally distributed. if you have to use them. So the parametric statistical tests we're going to be using, that is the t-test, the ANOVA, the F-test you're going to have. They require that before you do any statistical test, before you test the level of the significance in using these tests, then the data must be normally distributed. And we'll see how we will be able to calculate normality of data when we go forth. Now, also in our classes, we did in statistics 1, we saw how we could convert the raw values to set scores. And we are able to come up with the standard normal distribution using those tables. And we are able to come from any score you are given raw data. You can actually convert them to the set scores. And when you convert them to the set scores, you are able to come up with the normal distribution curve, that bell-shaped curve. I just want to draw something here so that we move together. That's a straight line up drawn. And we know the normal our normal curve falls on this. And we know that the standard deviation that will come here we have the standard deviation that comes here at the middle here, and the mean also at that point will be equal. So in a normal curve, when you move one standard deviation to the left, or you move one standard deviation to the right on that line, from that center, the line I've drawn there, or also move one standard deviation, two standard deviation to the right, or move two standard deviation to the left. The standard deviation at the center there, we usually presume that is 0. So when you are able to move one standard deviation to the right and one standard deviation to the left, then be able to move one standard deviation, two standard deviation to the right, and also move two standard deviation to the left, and also move 3 standard deviation to the right, and also move to standard deviation to the left. I'm going to bring us the normal curve and see what I'm trying to talk of at this point. I wanted to show us that we are moving one standard deviation to the right and one standard deviation to the left from the center of the normal curve. So this one you can see it is the horizontal line down there. We have 0 in the center. That's where the symmetry of the curve, when you fold it at this 0, then you'll have the mirror image of the left having the mirror image of the right. Now, when you move 1 standard deviation to the right, then you move 1 standard deviation to the left, that is -1. And on the right, you have 1. That area of the normal distribution curve is always 68%. That area of this, the normal curve, the distribution of that area of the normal curve is always 68%. So all the values that will lie between 1 standard deviation to the right and 1 standard deviation to the left will occupy 68% of that area. Then we move to 2 standard deviation and 2 standard deviation to the right. Then we see the area also. Now, when you move to standard deviation to the right, and you move to the standard deviations to the left, the area that will be occupied by the normal curve, it's 95%. And I've said up there that the values are within 2 standard deviation, STD, 2 standard deviation. Then when you move to 3 standard deviation, then the curve will occupy 99.7%. And this is within 3 standard deviation to the right and 3 standard deviation to the left. So the area, so we have now that area that is remaining will not be occupied. And this is what I'm trying to say. In this one, it's a rule, we call it 68, 95, 97, 99.7 rule. When you are moving the standard deviation, and here I'm using the standard deviation in the middle. So you are moving 1 standard deviation to the right, and you are moving 1 standard deviation to the, that's why I'm taking standard deviation minus mu and standard mean plus the standard deviation. So you will see this area that is occupied by this rule, it is 68.27, 95.45, and 99.73. So put these rules at the back of your mind, because this was the introductory part of this course. So when we'll be meeting next time, now we will be starting now the calculation and the tests that we are supposed to carry out using the parametric tests, so that when you are given some data, the first question to ask ourselves is this data following the normal distribution? Now, when you are applying this rule to, when you're applying this data, when you are applying this parametric test to this data, and when we are interpreting this data, will it be a representative of the entire population, or it will be a wrong representation of this population? So those are some of the questions we're going to ask ourselves as we'll be moving ahead, as we'll be doing the assumption, because when you're doing the tests, parametric tests, using using some rules here and there, we need to ask ourselves, and we need to know whether when you are doing the assumptions, whether we are inside the assumption or we are not having this. So that's why it was very important for us to bring in the last lesson and today lesson, so that we can do the introduction, so that when we start doing our calculations, when we are doing our assumptions, we are within what we are supposed to be, so that when we are doing it, we are not so bad off. When we are talking of the data should be normally distributed. And also we will be using SPSS. I'll be able to show us on how we can use SPSS to calculate normality of the data. Before you start, those are some of the prerequisite. Before you start doing the analysis, those are some of the prerequisite things you are supposed to do to see the assumption to all these parametric tests we are going to use. Pamela had asked me to send the notes prior to the lessons. I'll be doing that. Today I sent them a little bit late to you people, but I'll be trying so much so that when I send the notes, you go through them, so that when we meet in the class, you'll have gone through the notes, so that you don't have so much trouble with the class, because no, this one is online, and sometimes I'm not having a board where I'm writing. It might be, but I don't think it's going to be so difficult for us, because we have already gone through this. That's good. I'll want to conclude the class today, and I don't know if there is anything from the class. Amadi?
Yes, Dr. I just appreciate.
Okay.
Thank you for the good lesson.
Yes, Ismail?
Dr. I want to really say I'm very grateful, because the approach that you've used of giving us notes and then you will go on with the lesson, it's the best approach. I'm so grateful, Dr.
Okay, thank you. Pamela?
Yes, Dr. I'm enjoying the lesson. I appreciate so much.
Okay, thank you. Let us have Samuel.
Well, it's well, Doctor. Thank you so much.
Thank you. Our new member, Justice Obwire.
I've really enjoyed the lesson, Daktari, and I'm very grateful.
Yes.
I think I will continue enjoying. Thank you very much.
So, Obwire,
Yes, sir.
please take my number and email me your and text me your email address.
I will, Daktari.
0724
07
24 700
0724
700
700
686
700
686.
700 686.
Yes.
Thank you so much, Daktari.
Just text me your email address so that I can add in the group, so that when I'll be sending the notes, you don't miss out.
I will do so, Daktari.
Thank you very much. So class, let us meet next Thursday. I'll be able to make the notes and send it early enough so that you can be able to go through, so that when we meet, there's no trouble. Amadi.
Yes, Dr.
I've seen you have unmuted. Do you have an issue?
Not really, Dr. I'm okay.
Okay, thank you very much. So let us meet on next Thursday.
Thank you, Dr.